So thank you very much for this kind and warm introduction. I'm indeed happy to see the Hausdorff Center alive and doing well. I'm looking here at kind of the people in the front row who have a lot of work. And but let me, I mean, I will talk about math, but let me just say that in the beginning it was not at all clear that this endeavor would be successful, not so much because of the quality of math which is here, that was clear, but perhaps because of a certain not yet fully existing trust among the people. I mean, we had a tradition of two different institutes, pure math and applied math. We were sitting in different buildings, and so we didn't know each other that well when we started this. And I remember that as one measure to build up the mutual trust, Karl Friedrich Bödegheimer, who's perhaps here, and I went to a pèlerinage to St. Augustine to visit Stefan Hildebrand, who since a long time had a very keen and bold vision on where Bonn mathematics should go, and we got his blessing, and then we could start. Work. Okay, so this being said, so please excuse me that I will not dwell more in memories, but start with the talk. So this is a subject, stochastic homogenization, which actually I started here for me it started here in Bonn 7 years ago when Antoine Gloria, who has been a co-worker of mine since then, now is professor in Brussels, was postdoc here. And over the years, it started really out as a question in numerical analysis. And over the years, it got a life of its own and in a certain sense went into a direction which was not foreseeable for us, and in a certain sense turned into gave a new twist to elliptic regularity theory, or even if you want, had a certain contribution to geometry. And so I would like, in my talk, I would like to show you a little bit this this path we took, starting from, let's say, a hands-on question in numerical analysis to something which I hope also kind of the geometers, at least, or differential geometers at least, can somewhat relate to. So, but this being said, let me first kind of give you a little bit of historical, well, I should have mentioned one name. So in the end, I will talk essentially about a new result with Julian Fischer, who's kind of a very good postdoc right now at the Max Planck Institute. So let me give you a little bit of a historical teaser on stochastic homogenization. So there's nice textbooks on stochastic homogenization, and if you read the introduction, they kind of credit the first implicit occurrence of stochastic homogenization to Maxwell. So in his famous treatise on electromagnetism, somewhere way in the back, he he gives himself a lot of kind of exercises, and one of the exercises is the following. So in the back of his mind, he thinks of so it's about conductivity, resistance, conductivity. So in the back of his mind, he thinks of a homogeneous medium, a slab filled by conducting material, and then by kind of elementary physics, you know that if you impose a certain voltage drop at the two plates, at the two exterior plates, then there will then a certain current will flow. The current density is homogeneous, and there is a clear proportionality between the voltage drop divided by the distance and the current density, and that's given by the resistivity, or 1 over the resistivity is conductivity. So that's the homogeneous situation, which is here on this side. And now he was giving himself the following exercise. Instead of considering a homogeneous medium, think of what we call heterogeneous medium. So a medium where the conductivity depends on the place where you are because it's made out of two components. And what he was thinking of was kind of spherical inclusions of one of the materials in the matrix of the other material, and the two having different bare conductivities. And now he was asking the same question. What can I say about kind of the effective, the large scale, the average conductivity or resistivity of this mixture, of this composite material? And it's intuitively clear that if this slab is sufficiently thick so that it kind of is larger than many distances between these inclusions, it will have something like an average resistivity or an average conductivity, which are just inverses to each other. And in fact, but since in these days you wanted to, and still you want to compute things, he was interested in getting the value. Okay, that's not that easily possible, but there is an asymptotic regime when you can actually write down an asymptotic formula. And that's the regime when this inclusion is very dilute, when kind of the balls are, the radius of these balls is much smaller than their distance, as I try to draw. Then despite the fact that the current density is no longer constant, you can do an asymptotic analysis, and the formula for the effective conductivity, K, is, you'll find in his text, as a function of the volume fraction P. So that's perhaps the first instance of kind of a stochastic homogenization in the literature, and done as a little exercise. It's a nice curiosity that Einstein, in his PhD thesis on Brownian motion, went through exactly the same type of mathematical exercise. Again, of course, it was just a small aside in what he did there to kind of explain the molecular structure of the atomistic structure of matter. But the homogenization, the stochastic homogenization problem he had to solve was physically completely different. It was not, the phenomenon of interest was not conductivity, currents, but the phenomenon of interest was viscosity, so the resistance of a fluid to being sheared. And again, he was kind of comparing a homogeneous situation to a heterogeneous situation, which came from the fact that you had these solid particles embedded in the fluid, which again kind of destroys the homogeneity, but again, you would expect something like an effective viscosity. And again, he got the approximate formula, and perhaps not surprisingly, he used the same letters, K, for these quantities, although viscosity perhaps is not naturally denoted by K. So viscosity here plays the role of conductivity in the other example. So those are just, in a certain sense, a little bit of name dropping. Nowadays, of course, the focus is no longer so much on finding explicit formulas, because in general they're not available, and you would only get them asymptotically in certain dilute regimes, as considered by Maxwell and Einstein. But you want to really kind of in a general situation, like when you have a composite and you're interested in its elastic properties, or when you have a porous rock and you're interested in its permeability, you want to get these effective. You want to numerically get these effective properties. And of course, nowadays you would resort to numerical simulation, and kind of the most natural method, which I want to explain a little bit better later on, goes by the name of a representative volume element, and where you sample in kind of a finite domain. You're on the computer, your medium, and then you do a finite number, actually equal to the number of dimensions, so 3 calculations, to get an approximation to the effective behavior. I'm going to explain that in a second. But this was the starting point for us. What's the error you make in this method? So that is what got us started, and in my talk I would like to explain how from this, or I would first tell you a little bit about this numerical analysis question, about this question which arises in kind of engineering computations, and then in the second part of my talk, I really want to switch gears and kind of give you a connection to elliptic regularity theory, or rather to almost geometry. So for those who might be not so much interested in numerics, or let me tell you that it will be about the dimensions of the space of harmonic functions of a certain growth, in how far these dimensions agree with the Euclidean dimensions, which is kind of a classical question in geometric analysis. Okay, so let me start with the first part on this numerical method. So let's first kind of find a suitable mathematical formulation of these problems in stochastic homogenization. So as you may have already seen, behind both problems considered by Maxwell or considered by Einstein, there's a certain type of partial differential equation hiding. So an elliptic, to be more precise, an elliptic partial differential equation. And elliptic partial differential equations are described by coefficient fields, by uniformly elliptic coefficient fields, which in a certain sense characterize these equations. If you're more geometrically inclined, you may think of kind of a Riemannian metric and the corresponding Laplace-Beltrami operator. Okay, so that metric, or this coefficient A, describes the heterogeneity of the medium, and there you on the slides you'll see the condition that this one is uniformly elliptic. So this gives rise to an elliptic differential operator, which, as I said, would be the Laplace-Beltrami operator in more geometric terms. So you take a function, you apply the gradient, then you get a vector field. You multiply with this tensor field, you still get a vector field. Then you take the divergence, and that's the kind of this elliptic operator. So random media means that in fact you don't have, if you want, you don't have knowledge about the details of your coefficient, which varies in space, but you have knowledge about a probability distribution on the space of coefficients. So what you have, and I'm going to use kind of the language which is used in physics, you have an ensemble, which just means you have a probability measure on this infinite dimensional space of uniform elliptic coefficient fields, and I will use this physics notation to denote this ensemble. And just to fix ideas, think of the following Poissonian ensemble, which is a little bit similar to what both Maxwell and Einstein considered, but this is just to fix ideas. Think of the following coefficient field. So you take a Poisson point process in d-dimensional space of density 1, which essentially means you place every point completely independently of the others, uniformly distributed, in order to achieve a density 1. And around each of these points, you put a little disk, if you're in 2D, or a ball, if you're in general dimensions, let's say of radius 1/4, so that there is not too much overlap. And then you look at the union, at this random geometric set, which you get from taking the union of all these things. So that defines your random set, and then you define a random coefficient in a very simple way. You just say, on this set it has one value, on the complement of the set it has another value. So let's say on the set it has, what did I say? It has the value 1, and on the complement it has a lower value lambda, which then governs the uniform ellipticity in the sense of the second formula, the formula in which I wrote down. So in a certain sense, stochastic homogenization or random media is about understanding random elliptic differential operators, like defined here. So in order to make a little bit more, in order to motivate this numerical method, it's actually useful to think a little bit in physical terms, just because it conveys the right set of mind and the right ideas. So let's go back to Maxwell's example, where functions had the meaning of the electric potentials, where the negative gradient of the function kind of indicates, according to Maxwell, the field. That's the electrical field, so the force which a charged particle would experience. And then if this coefficient field A denotes the conductivity, then in order to get the current which flows through this medium, you have to multiply the field with this matrix. That gives you then the electric current. And this electric current is stationary, doesn't lead to the accumulation of charges if it's divergence-free. And this is how you should think about the elliptic equation. So looking for an aharmonic function, as I kind of wrote down in the second paragraph, really means you're looking for an electric potential that is such that it leads to a current that is stationary. So this is how you could think of harmonic functions. And now what's the merit of the homogenized coefficient? Well, the homogenized coefficient relates the average, the large-scale electric field, to the average, the large-scale electric current. That's the kind of the effective information which you want to extract from the medium in order to simplify your model or to make kind of theoretical prediction. So it's a linear operator which goes, it's a matrix, a hom, which goes from fields to currents. Right? That's the effective behavior. And now the big question is, on the one hand, you have your statistical rule, which I explained, like Poissonian ensemble and so on. And on the other hand, you have these, in 3 dimensions, 6 numbers. Typically, it's symmetric, so it's 6 numbers. You have this one matrix. And out of kind of this world of statistical information, you want to extract these 6 numbers. And there's no simple formula for that unless you're in an asymptotic regime, dilute regime, like, or certain special cases, like Maxwell or Einstein considered. So that's the question which you face from a numerical point of view. So what's the representative volume element? So I already said that very roughly in the beginning. You sample your material according to the rules which you have been given on a finite domain. And the best is to take a torus. So to kind of identify, let's adopt 2-dimensional language, identify the lower and the upper side and left and right side of the square. And on this torus, you use exactly the same rules to get your material. So you take the Poisson point distribution on the torus. You do your disks. You look at the union, and then you get a sample of your material. Now you're on the torus. Now on the torus, it's easy to impose an average field. You do that by taking the ith coordinate direction and then add to it the gradient of a periodic function. Because the average of the gradient of a periodic function always vanishes, that gives you always kind of something which has, as I kind of, let me see whether this works. No, I'm not so good at this. So let me try to use the pointer. Aha, this doesn't work for some technical reasons. It works only very dimly. So here you see. Here's what I just said. And then, yeah, but I'm too. My hands are too shaky, nervous. Thank you to do that with the mouse. Not because of you, but. Let's see. No, this is really a bit. Perhaps I can try to do this like this. So this is now this is the equation. So this is the electric field, which has the property that it has an average which points, let's say, in the first coordinate direction. So that's indeed an electric field because it can be written as the gradient of a linear function plus a correction. By the way, this is called corrector. And now you want this field to give rise to current, which is stationary. So you look at this equation, and now you get, so this defines a problem which once you discretize, you can, let's say, easily solve because you're looking for a kind of a periodic function which solves this elliptic equation with this right-hand side. And then you take the average current. So this is the current which comes from the problem. You average it over the periodic cell, and you take this as an approximation to your effective behavior. And of course, you expect this approximation to be good when You expect this, this approximation to be good when L is large. So if you think about it, just without doing any calculation, you realize that there are two origins of error you're making. So here again, on the first line, I wrote down how this approximation to the effective behavior is defined. And the first thing to notice is, of course, this answer still depends on the realization you've taken. I mean, here I've given you 3 different realizations of the random medium, and each of them will give you a different answer. So the answer is still kind of a random variable. It's still fluctuating. It has a non-zero variance. So that gives kind of, that's the first source. That's the first source of error. Of course, you expect that as you make L larger, and here I didn't make L larger, but I rescaled my picture, which mathematically anyway doesn't make a difference. So if you make L larger, then these fluctuations, the variance of this random variable, which is taken to be a good approximation, of course you expect that this goes down because there's more and more self-averaging taking place. So that's one source of error, fluctuations because you're looking at a specific sample, a specific realization of your stochastic specifications. But there's a second type of error which is a little bit more subtle. So even if you completely disregard the problem with the fluctuations, if you would look at the expectation of the numerical answer you got, for instance, by doing many, many realizations and taking the empirical average, then you would get a good approximation to the expectation. Then you would say, well, the expectation, that should be fine. I mean, as soon as I get the expectation, no matter how large L is, I get the right answer. Because after all, if I sample my medium on a smaller portion, it exactly looks like a subset of my larger portion. But that's not the case, and is easily seen if you take kind of the smallest representative volume element and you extend it periodically, because this is in the end what you're doing, you see that you have introduced kind of long-range, artificial, spurious long-range correlations in your medium. You falsified your statistics by going to this finite volume element, and that's kind of a bias, a second type of error. So why is it interesting? So here's a summary of what I said. So so you have these 2 types of errors. One just comes from the variance of the numerical answer, and one is the deviation in the expected value. Of course, by Pythagoras and probability, you have on the level of squares, the total square expected error is the sum of the square of the random and the systematic error. And qualitative theory tells you both errors go to 0 as you make your representative volume element large. So why is it of interest to understand the rate at which it goes to 0? Well, this is because something I already mentioned before. You have a second, when you're doing numerical calculations, you have a second knob to turn. You, at the beginning, I mean, at first, you're free to choose the period of your representative volume element. The second degree of freedom you have is the number of samples you're taking when you're taking the empirical average. So you have two degrees, 2 decisions to take. And then, of course, you may ask the question, what's the best way to spend my unknowns? What's the most efficient way to spend the number of operations or the time I want to wait till I get the result? Is it better to just look at a few samples and at an enormous size? That looks good because it reduces both the systematic and the random error. Or is it better to just look at kind of at a fairly small sample and a small periodic box, a small size of your representative volume element, and then do many realizations and take the empirical average over many realizations? That looks also good, but one has to keep in mind that this just reduces the random error, not the systematic error. So if you, oops, right, so yeah, back to the slide. So you see that there is an optimization. If you understand how both the random error scales in L and the systematic error scales in L, then you can find the best way of spending your of getting a certain precision at a given cost. So therefore it's of interest to get a good understanding about these two types of errors. So now, surprisingly, this is a hard thing. So stochastic homogenization, the qualitative theory, I glossed over it, is, I didn't mention explicitly kind of the three most important names of people who introduced kind of the qualitative theory. In the West, Varadhan and Papanikolaou, in the East, Kozlov. The qualitative theory of stochastic homogenization is from the late 70s, so it's 35 years ago, and but it's a qualitative theory, and getting these error estimates kind of requires quite a different set of ideas. So the first result in that direction was like Kozlov from Moscow, Jurinsky, kind of about 10 years after the qualitative theory came about, was the first one to come up with rates, but they were suboptimal. He didn't get the right exponents. Then again, 10 years later, there was an interesting development, which I think in the applied community got completely unnoticed, which came from statistical mechanics. So Tom Spencer and a student of his, Ali Nadav, were interested in a completely different question: fluctuating surfaces, thermal noise, not quenched noise, fluctuating surfaces, and they wanted to understand kind of the correlation. And they realized that in order to give the statistical mechanics question, they were drawn to a problem in stochastic homogenization. They wrote a famous paper on that. And then they realized, oh, but we can actually also learn something on quantitative stochastic homogenization. They wrote a second paper which was rejected, but which luckily made it to the web, and we found it. And so that was a very insightful work, but it gave you, it just gave you the optimal rates for a very low contrast medium. So if the lower and the upper bounds on your matrix are very close to each other, because for the experts they use Mayer's estimate as a crucial ingredient. And then in a certain sense, together with Antoine and a couple of other people, we made a career out of kind of extending this, extending these ideas to the case of arbitrary viscosity contrast. And so the story goes on. More recently, people around Scott Armstrong, Charlie Smart, Jean-Christophe Murat, and others got kind of revisited this question and kind of put a different perspective on it. They didn't just want to get the optimal rates, but also the optimal stochastic integrability. Gaussian bounds is what you would expect. And there is still kind of, we haven't completely solved the problem, because with our methods, which are more inspired by statistical physics, functional inequalities, logarithmic Sobolev inequalities, we get the optimal rates, but we fail to get the optimal stochastic integrability by a factor of 2. We get exponential bounds instead of Gaussian bounds. They get the, by a completely different, more variational method, they get the optimal stochastic integrability, but they don't get the optimal rates. So in a certain sense, we still have to find common ground to get both, at first the rates and then also the stochastic integrability. So here's the result, which doesn't care for the stochastic integrability, but just for the optimal rates. So the random error essentially goes like the central limit theorem scaling. So if I take the square root of the random error, it goes like 1 over the square root of the volume. That's what you would call central limit theorem scaling. Whereas the systematic error is much, much smaller. Up to a logarithm, it's the square of the random error. So the message is, it indeed makes sense to look at a large number of samples, because you have to first worry to make your random error small, because it's much larger, by sampling a lot, and then only afterwards you have to worry about kind of making your systematic error small. So that gives kind of a precise answer here. And I'm being very cavalier in kind of quoting the argument. The first part, the random error, has been established under many circumstances, which include the example which I gave you. The systematic error, in fact, we established for a discrete model, discrete IID model, but we strongly believe that it can be extended to the framework which I'm saying. And in a certain sense, the story goes on. Jim Nolan and Antoine Gloria have, in fact, then shown that the random error not only has this central limit theorem scaling, but itself as a random variable behaves Gaussian. So, so in a certain sense, that's already a next order result. So we now have the tools to give these precise questions, precise answers. So this was our motivation. So now I would like to shift gears and come to the type of question into which this, in a certain sense, degenerated, which have nothing to do with numerics, but rather with regularity theory or geometry. And I should ask my chair how much, or I can look at my watch myself. So I still have about 15 minutes. Is that correct? It must be, okay. 30 minutes. Oh, right. Okay. 20. Okay. So so let me come to this to the second part, which I said is a completely change of perspective. So so again, but our objects again are these uniformly elliptic coefficient fields on RD, as described by this metric. And now, since I'm perhaps talking more to the geometers, think of kind of a metric tensor, at least in dimension larger than 2. You can it's as kind of an as valid viewpoint, and this condition would tell you that you're looking at a geometry which not has just the same topology. I mean, you don't just have the topology of RD, but also all your distances are comparable to the RD distances. So your intrinsic distance with respect to this matrix A is in the large and in the small always comparable in terms of upper and lower bounds to the Euclidean distance. And then, as is kind of very common in the field, you can ask the question, well, consider the space of all harmonic functions. So here I mean harmonic functions, intrinsically harmonic functions, so solutions of Laplace-Beltrami, u is equal to 0, or aharmonic functions for the analysts, so meaning solving this elliptic equation with inhomogeneous coefficients, that have a certain growth exponent slightly less than alpha. Alpha doesn't have to be an integer, and I don't need to impose the growth in a pointwise sense, but just in the square average sense. And now I can ask, or people have asked the question, and I think, for instance, that originated in a paper by S.T. Yao, but I don't know whether that was the first paper which asked this question in this specific sense. When is it true that the dimension of this space is the same dimension as in the Euclidean case? So the Euclidean case, of course, we perfectly understand. I made two kind of pictures here on the bottom to explain that a little bit. So this is the alpha axis, so that's the growth rate. If you're looking at harmonic functions which have sublinear growth, so for which alpha is 1 or less, of course you just get constants. If you go to subquadratic, you get the 3 linear functions in 3 dimensions. If you go to subcubic, you get all the quadratic, in addition, you get all the quadratic polynomials. So kind of the dimension of these spaces kind of decreases, increases in well-defined steps, and of course you can write down the formula for that. That's the Euclidean case. And now you can ask the question, under which conditions on my geometry do I have exactly the same dimensions? Under which conditions on my geometry do I have this rigidity? I mean, under which conditions on my geometry does it look like the Euclidean geometry from the viewpoint of harmonic functions? And so there is one nice result which tells you that under essentially under no other conditions than this uniform ellipticity, you get the same asymptotic bounds. Kind of to if you ignore the value of the leading order coefficient, the leading order exponent, the leading order exponential factor is exactly the same as in the Euclidean case, no matter how your coefficient field looks like. And that uses kind of the technology of volume doubling, Poincaré inequality, so all this technology which ultimately arose from Nash and Moser and de Giorgi. But on the other hand, so this is kind of a soft answer for this question, but on the other hand, if you really ask about equality of the dimensions, then it fails. And it fails already as soon as alpha is positive. So it's very easy to come up with a coefficient field which has the property, uniformly elliptic coefficient field, which has the property that it allows for harmonic functions which grow like a root. And so in analysis, that's known in the framework of quasi-conformal mappings. But in geometry, I think that's very intuitive, because it's, in a certain sense, you should think of a metric cone, which has a too large of a circumference, as I tried to indicate there. And then you find very explicitly a harmonic function which grows like the alpha root, so which has sublinear growth, which means that the space of the harmonic function that have sublinear growth has dimensions larger than 1, so it's not the Euclidean value. And now, in analysts, we're typically used to stare at the singularity, so of this metric at the origin. But you can smooth that out. So it's more the large-scale behavior that's only the large-scale behavior that's of interest to us, and you can smooth out the local singularity of the coefficients, and this survives. So you have a complete lack of rigidity when you ask the precise question about equality of the constants. And but then the famous result of Nash and DeGiorgi can actually be rephrased in this matter. So they in a certain sense proved by their Harnack inequalities, or in a certain sense rather the C alpha a priori estimates, that for a given ellipticity ratio lambda, there exists a small growth exponent alpha 0, which just depends on dimension and lambda, which might be extremely small, that your Liouville principle holds up to this small exponent. And, but that exponent depends on lambda, and it goes to 0 as lambda goes. So that's a reformulation of this famous theory. But in systems, it's even worse. And what I'm going to say includes the case of systems. In the case of systems, you can find harmonic functions, you can find uniformly elliptic coefficient fields which allow for harmonic functions that go to 0 at infinity and are not constant. So the systems case is even worse. And it's interesting because what I'm saying is, in a certain sense, blind to whether it's scalar or a system. Okay, so now I would like to tell you how we came up with criteria on this rigidity, and how it's connected to stochastic homogenization, and how it tells you, in a certain sense, that generically things are well behaved. And that's related again to that's related to harmonic coordinates. So again to looking at certain, like in the numerical method, looking for the I coordinate direction, looking at these harmonic d-harmonic functions, which you think of harmonic coordinates, and the criterion is formulated in terms of the scalar and the vector potential of these harmonic coordinates. So this is, for most of you, this will be very easy, little bit of exterior calculus. So if you have a harmonic function, then its gradient is a closed 1 form. But if you multiply it with a metric, you get a closed d-1 form. So since you have a closed 1 form, you have and since topology is trivial, it's the exterior derivative of a 0 form. Perhaps I should go up there again. And that's exactly what plays the role of the corrector in kind of the numerical analysis, and I wouldn't have to use exterior forms to make the point. But for the closed d-2 form, the current corrected by some constant factor, it's actually more telling to think in terms of differential forms. So you can write it, so this closed d-1 form you can write, of course, as an exterior derivative of a d-2 form. That's what I would call, in 3D analogy, a vector potential. And in my poor man's analyst version, I can represent it as a skew-symmetric matrix, and I can write this vector field here as the divergence of this. This is just kind of equivalent. And the important, so the type of criterion that implies this dimensional rigidity, these Liouville theorems, has to do with the sublinear growth of these corrections to those are corrections because I subtract constant vectors, corrections to the scalar potential and to the vector potential of the harmonic 1 form or the harmonic d-1 form. So if they grow sublinearly, then I get something. And that's exactly our kind of first result, which is just a deterministic result. So so we're interested in kind of these spaces of harmonic functions of a certain growth. We have these, for every coordinate direction I, we have a scalar potential, and we have the vector potential, which is a skew matrix. They're related by this equation, which I wrote down. That's just what I said before. And